which we received two components, X filter desired plus V residual noise. Okay, so if we want to get distortionless response, which means that the output of the filter, we get the same desired signal, you see. So we need to add a constraint that H, the filter that is applied to the relative transfer function, the steering vector here, will be 1 for all frequencies. And then we assure that X filter desired will be equal to X1. So this is the distortionless constraint for this model. Okay, so what I want to talk before we continue, so we talked about the MVDR. So the MVDR, actually what it tries to do, MVDR, minimum variance distortionless response. So what we try to do is to minimize the variance of the residual noise, which we try to minimize using H for each frequency. We try to minimize the variance of the residual noise, which is H phi V F H, subject to the distortionless constraint. And we said that it's also equivalent to minimizing the power of these two. Instead of minimizing the power of the residual noise, the variance of the residual noise, we can minimize the variance of Z, which is equivalent. Okay? So instead of minimizing the variance of the residual noise, we can minimize the variance of Z, which is actually H F phi Y HF, subject to the distortionless constraint. Because under this constraint, minimizing the variance of the output of the estimate is the same as minimizing the variance of the residual noise. Because this is X1. Okay? So if we try to minimize the variance of X1 hat F magnitude squared, so it's equivalent to minimizing the variance of V residual noise magnitude squared. If both are under the distortionless constraint. So if we have the distortionless constraint, both produce the same filter. It's the same. And actually, it's not the same if we have estimates of the coherence matrices of V and Y. But otherwise, these two produce the same filters. But in order to distinguish between them, sometimes we call this minimum variance, minimum power distortionless response. Okay? minimum power, distortionless response. So if we know exactly, if we don't have error in this coherence function matrices, if we know this and this accurately, no error, so the filters that we find using the MVDR or MPDR, that's the same. But if we estimate this, then generally they will produce different results. And you can ask which one is better, which one is more robust, and so on. Okay, so there are some works that talk about this, the relation between them and which one produces better results under which condition and so on. Okay, but I just want you to know that there are some differences when these matrices are obtained by estimates. Okay, and then we continue and we talked about LCMV. So for LCMV, linearly constrained minimum variance, what we try to do is to minimize the variance, minimum the variance, which is to find a filter that minimizes the variance, H subject to not only the distortionless constraint, but additional constraint. So we have some constraint, which we put in a matrix, C. This is the C. This matrix contains the constraint for each frequency, and multiply with F, and this equals to some values, some vector, whatever. We call it, let's call it I vector of constraints, these values. Okay? And we found a solution. Okay, but I don't want to talk about the solution. It's not difficult to find the solution. Well, already we showed what is the solution, but I want you to see the equivalence. Now, instead of minimizing the variance of the residual noise, we can minimize the variance of the estimate. It's the same under these conditions, as long as this constraint, one of them includes the distortionless response constraint. So if in these constraints, one of them includes this constraint, so we can minimize, instead of the variance of the residual noise, the variance of the estimate, of the output of the filter. So we can write it like this. Okay, so the same thing like here, we call it linearly constrained minimum power, if we want to identify between them. But sometimes people call this also LCMV, and they call this MVDR. But sometimes people call it MPDR, and this LCMP. But now we understand. Okay, so theoretically it's the same, but in practice it's not the same. Okay, now suppose that we want to implement these problems. You see, suppose that we want to have the same solution of MVDR or, or MPDR or LCMV or LCMP, okay? Suppose that we want to get a solution, but in a different way. So as you know, when we give different expressions or different derivations for the filter, maybe theoretically it's the same, but in practice it's not the same because of different implementations, different way to derive the filters, different ways to adapt the filters for changing environment and so on. So it's important to derive filters by different methods, okay? So now I will talk about different methods to derive this solution and this solution, okay? These solutions, which is very important because actually many times in practical environments, especially non-stationary time environments, it is more useful, okay? So first, okay, so maybe, okay, so you remember this. I don't need to keep. I can delete it, and if we will need it, I will write it again. But before that, I would like to talk about adaptive filtering, okay? What is adaptive filter? Adaptive filter is when we have a noisy measurement and we have another measurement of noise that correlates with the noise in the measurement, okay? So I will give you an example, okay? So I talk about adaptive filtering. Okay, so suppose that we have a noisy measurement, yt equals to xt plus vt. So this is like the single channel, okay? Single channel noisy environment. But in addition, we have another channel, RT, which correlates with the noise, but it's uncorrelated with the desired signal. So we call it reference channel. So this is a reference channel. Okay, so suppose that we have this problem. What do we do? Of course, we can ignore this and only try to estimate xt from the noisy measurements, just like we did with the single channel. But if we have another channel such that RT is not uncorrelated with the desired signal, only with the noise, so we can take that into account. What do? We try to find a filter, WT, okay? So what we try to do is we try to obtain an estimate of t, x, of the desired signal. How? So if we knew the noise, what could we do? Okay? So if we knew what is the noise, we could do something like that. We would like to estimate the noise and suppress it from the signal. Okay? So here what we can do, we take yt and subtract. We want to subtract the noise, but we don't know the noise. But what we can do is to find a filter, let's call it WT, such that WT convolved with yt. So this will be, with RT, with RT. So this will be an estimate of the noise. So we would like that this will be an estimate of the noise. So this will give us an estimate of the signal. Okay, of course, we can try to do that. Sometimes if it's not successful, we need to find out why it's not successful. But something like that is called adaptive filtering. Okay? And the thing is, how to find the optimal filter here. So what is the optimal filter? So it turns out that the optimal filter is obtained by minimizing the variance of the measurement, of the output of the adaptive filter. Okay? So this is what we want to achieve. So how do we do that? Suppose that we have a noisy measurement and we have a reference channel. We can find a filter WT such that Y minus RT convolved with WT will generate an estimate of the desired signal. So we minimize the power at the output, and we can adapt this filter. So this filter, this is the way to write it, like this. So this filter is obtained by minimizing the power at the output. That's why it's very important that RT, the reference channel, is uncorrelated with the desired signal. Because if it's correlated, maybe it will minimize this power, but minimizing the power of the desired signal. But because it's uncorrelated with the desired signal, it means that the only way to minimize the power here is by minimizing the residual noise. Okay? Because the power here, you see, I can prove, the power here, the power at the output, contains the power of two components. One component is the filter desired, and one component is the residual noise. So if we try to minimize the power of this, and the reference is uncorrelated with the desired signal, so it means that the only way to find a filter that will minimize the power here is by minimizing only the residual noise. It will not affect the desired source, the desired signal. Okay? So this is called adaptive filtering. And of course, we can do that similarly in the frequency domain. So I will show. You see, this board is relatively small. So maybe this part. So I will write it here. So we can do that the same. So we can write that YF equals to XF plus VF. And we have our reference channel in the frequency domain. So we have two channels. And then we try to find an estimate, ZF, which is an estimate of XF for each frequency, by taking YF and subtracting a filter, WF, that multiplies RF. And we need to find the optimal W, but by minimizing the variance of ZF. Very nice. So the block diagram is similar. Okay, similar, but instead of T, there will be F. So I don't need to write it again, the block diagram. It's the same, but with frequency. Very nice. So this is like reminder about adaptive filtering. Now suppose that we don't have a reference channel with a noise-only component. So here I assume that with one sensor I measure desired signal plus noise. In the other channel I measure just noise that is correlated with the noise in the measurement. But suppose that I don't have that. I have two channels. Both of them contain the desired signal. What do I do? Okay? What do I do? Let's think about it. Okay? So out of place, I will delete all of that. Okay? So now we proceed that we don't have what we call a clean, sometimes we call it a clean reference channel, even though it's noise, only noise. Because a clean reference channel, when we talk about reference channels, we mean that it contains only noise. And if it contains the desired signal, we say it's not clean enough, even though it's the opposite, like it's only noise. But this is the way we speak, because for the reference channel, if we have the desired signal in that channel, it means that it has something that interferes with our filter. That's why when we talk about clean reference channel, it means that it contains only noise. Okay, so now we talk about the problem that we don't have a clean reference channel. It contains some part of the signal. So let's assume that we have Y F equals to XF plus VF. This is the main channel. And we have a reference channel, another channel. Let's call it YRF. So it's another channel, reference. So we would like that this reference channel will contain only noise. Of course, not the same noise. If we have the same noise, that is great. We just subtract, okay? But we don't have exactly the same noise in the other channel, in the reference channel. So we have some noise, but we have also some level of the desired signal. Usually it's low, but we have something. So we can write here, let's write it as GF, XF. Usually G is small because in the reference channel the desired signal is much lower. But we make a general estimation here, okay? Plus noise. Oh, okay, we use W for the filter, so let's use something else. Let's call it VR, okay? This is the noise in the reference channel. Okay? What do we do? If we try to do what we did before, it will create a large distortion at the output, so it's not good. So now we cannot do something like that. So I will show you what we did before. YF, here YRF, and then we want to find a filter. Here minus, here plus, and here X hat F, okay? This is not a good solution. Why? Because if we try to adapt or to find W such that the energy here is as low as possible, what will happen? W will try to minimize the energy here, the variance here, by filtering also the desired signal. So this is a wrong solution. So I said bad solution, okay? So this is a bad approach. It's not good. So what do we need to do? Okay, what do you propose to do? Simple. You know, in mathematics, there is something like that. Okay. Suppose that there is, soon you will have a tea break, okay? So suppose that there is a tea can or bottle or something like that, and you tell to a mathematician and a physician to take the bottle and pour some tea to the glass. And they are in the same room, okay? So the mathematician will come and pour the glass, you solve the problem. The physicist will do the same. Now suppose that you take both of them and you put the bottle next to them, like here. So the physicist will take and pour the tea to the glass, okay? The mathematician will go to the other place and say, this problem I already solved, okay? So he doesn't need to solve another problem, okay? So this is like a difference between a mathematician and people who work with physics, okay? So we know the problem that we solved before, okay? So let's try, instead of solving this problem, let's come to the problem we solved before with the adaptive filter. So what do we need to do? Here we have a reference channel with some desired signal. So what do we need to do? Is to create a reference channel without desired signal, right? And then the problem that we solved before, we know the solution. How do we do that? Okay, so from these two, do you agree that we can create a reference channel, RF, that doesn't contain the residual, doesn't contain the desired source? How do we do that? What? Yes, we can use both of them. Exactly, so we can get the correlation. So the correlation, if we know G, suppose that we know G, okay? So what will we do? Very simple. We will take GF, multiply it with YF, and subtract YRF. Can we do that? Suppose Y and YR are our measurements. And G, suppose that we know how to estimate this correlation. Assume that we know. So what do we get here? GY minus, so this is cancelled, the desired signal. So what we have is G VF minus VRF. Do you agree? So now we're back to the previous problem, that we have two channels. Now we can use Y and R. So we can use the main channel plus reference channel that contains no desired signal at all, only noise. And then we can find solution, but instead of YR, we will use R. So how do we do that? You see, we multiply so we have YRF. So we multiply this with G. Okay? We multiply Y with G. And then subtract it. Here it's plus, here it's minus. Subtract the other channel. So here we get RF. And now we find an adaptive filter such that it minimizes the energy or the variance at the output. And then we get X hat T. Okay? Any questions? Okay, so this is a nice approach. Now, to produce R from the two channels, we can write it like this, you see? So we can write RF as GF minus 1 YF YRF. Okay? I write it like this. So this part, which is here a vector, but generally we will show that is we can do it because here we have only two channels. If we have more than two channels, this will be a matrix. Okay? So this is called blocking matrix. So blocking matrix means that we take the multi-channel signals and we create, generally here we create, if we have M channels, M sensors, we create M minus 1 channels that contain only reference, only noise. So this will be reference channels. Okay? So in our case, when we talk about M sensors, so we have M sensors for the frequency F. What we need is to find a blocking matrix and this, okay, so here we have M and the output will be M minus 1. So here we have RF, and RF is the size is M minus 1 because we want to cancel the desired signal. Okay? So it means that in this M minus 1 channels, we only have reference channels without any signal. And here we can find a filter, WF, And generally here, we can add a certain filter. Let's call it H0. I will talk about it. And then here we take plus, minus. And here we have ZF, which is an estimate of X1F. And how do we find this filter? By minimizing the power at the output. So if we minimize the output of the variance at the output, it's similar to minimizing the variance of the residual noise at the output. Why? Because these channels, they don't contain any desired signal. So the only possibility to reduce the variance at the output is by minimizing the variance of the residual noise. So this is all the concept of adaptive filtering, and we will talk about GSC in a moment. Okay? So one of the earliest methods that was used for such a thing, actually even without blocking the desired signal. Actually, one of the earliest methods, in the past, people wanted to measure the heart rate of a fetus inside when prenatal, inside the uterus. So do you know how it is measured today? How is it measured? The heart rate. So you work all in signal processing. You don't ask yourself how maybe sister, mother, how something is measured? You are not curious? You see that, okay? When you go out to hospital and a pregnant woman, so they measure the heart rate. So how do they measure? Okay, try to be more curious. So when you see things with signal processing, try to think, okay, how is it done? What do you think? How is it done? How? Okay, so before I talk about how is it done today, I will talk about how it was done long time ago using signal processing. And when you think, okay, long time ago, when was it? Try to find when was it, because it's good also to know some history, when it was implemented. So it was not like 300 years ago, okay? Signal processing. So try to think how it was done in the past and when was it? And what equipment did they use to measure, for the measurement? Okay? So when this kind of signal processing was used, they used actually two microphones. Two microphones. So they put one microphone near where you get the desired signal. Okay, you see where we delete all the time. So we want to measure, so this is the main channel. This is the main channel. So we want to measure to find where to put the microphone with the largest amount of desired signal. What is the desired signal? The heart rate of the fetus, yes? Okay. So where to put it? Where to put it? Here, here, here. Where to put? Where do you think? What? Abdomen, but where? Down or up? Down. Okay, it's partially good. Yes, but it's good. Good answer. Most babies, the head is down. So you want to put the microphone close to the heart, which is somewhere in between the shoulders. So if the head is down, you will put it down. But if the head is up, probably you need to put it in a higher place, at the top of the abdomen. Okay? So you need to try where the pulse, the heart rate, the pulse, will be strong. So you need to put the sensor, the main channel, where you can get the strongest desired signal. Okay. What is the noise? So we have different types of noise, but what is the main interference? Exactly, the mother heart rate. So what do you need to do? You can add another sensor, another microphone, and put it next to the heart of the mother. So maybe it will have only reference, only the heart rate of the mother, and the heart rate of the baby is negligible. Okay? And then what you need to do is something like that. So if the other reference signal, it doesn't contain the heart rate of the desired signal of the baby or the fetus, so we are good with this solution. Otherwise, we need solution like that. So we need to block the signal. So we need this G. So maybe it's not easy to find it, okay? But what they did in the past, they ignored this part, and they assumed that the other microphone, with the other microphone, we have only the heart rate of the mother. So why don't we just subtract one from each other? Because it's not the same, okay? So the heart rate in the other sensor, it's not the same as the heart rate of the mother in that signal. But they correlate to the same heart, the same source, okay? Same source. So this is how initially, how they did that. So that was one of the early uses of adaptive filtering, which is nice. Now, okay. By the way, for heart rate, sometimes they don't need exactly that it will contain. So it's sufficient that they significantly increase the signal to noise ratio. And then they can listen to the heart rate of the fetus. Okay? Because even in the microphone, when they measure the desired signal, the noise, the heart rate of the mother is much more significant. That's why they need to do some adaptive filtering, okay, which is really nice. Now, nowadays, the sensors are completely different. You can even take one sensor. You don't need two sensors. How do they do that? Okay, I'll give you a clue. Using ultrasound. How is it possible to measure heart rate of a fetus in the abdomen using ultrasound? Not ultrasound when you take a video of the ultrasound, but the ultrasound signal. So I remind you, what do you do with ultrasound? You transmit a signal, you get it back. Okay, so you transmit a signal, you get it back. What happens to the frequency of the signal that is back, received back from the target? It depends on the movement of the target. So we get a Doppler. And using this frequency difference, we can measure the movement. So this movement gives us a measure of the heart rate. Okay? Next time when you see devices, try to think if it's related with signal processing. At least, if it's not related also, you can ask questions. How it is implemented, what is the main concept over there. So it's interesting to know. Okay, now how this is related to MVDR. So this is a very nice way to obtain MVDR differently. Okay, so it's a different expression or different way to achieve MVDR using such a structure. This structure is called GSC, Generalized Side-Lobe Construct. There is a very nice paper, only 4 pages. So if you have time, read that paper. It's number, in this chapter, is number 17. Okay? Only 4 pages about the equivalence of LCMV and GSE. Nice paper. Okay, even though the mathematics is similar to what I show you on the slides, but I think it's really good to get used to read papers when you want to find something. So you see all the paper, you see the structure, how they present the work. So it was published in 2002. Okay, 22 years ago. By the way, it was also developed before, but this, they show a very nice equivalent, so it's a nice paper. So what do we do? With the MVDR, what we did, we minimize, I remind you, we minimize the variance of x1, the variance of the output, okay, MVDR. We minimize the variance of the output, which is H, F, phi y, HF, subject to distortionless constraint. Now, instead of using a filter, so here the output Z equals to H Y. Okay? So instead of using this structure, what we did before, see, here we have Y, we multiply with H, we get ZF. So instead of writing H this way, we write H this way. So this is kind of block diagram of the implementation of H. So here we can write H using this GSC, generalized sine law transfer. We write it as H0F minus B WF. Okay, so we can always write something like this. Okay, so it looks like we try to solve a more complicated problem. See? But actually it's helpful, as we will see. But it looks like we complicate the problem instead of simplifying the problem. Usually we look to simplify problems, not to make it more complicated. But the objective here is like that. So we can show how to find H0 and how to find W and how to find B. Okay? So H0 we find such that it satisfies the distortionless constraint. So H0 is such a filter that satisfies any filter that satisfies the distortionless constraint. The blocking matrix is a matrix of size M by M minus 1 such that we have here M minus 1 channels that don't contain m linearly independent channels, okay? So this is the dimension. We started with m channels. Now we have m minus 1 channels. So these channels, they don't contain the desired signal. So we call it, actually we call it something like that. So this is blocking matrix because it blocks the desired signal at the output. And the maximum channels that we can get out of m channels without the desired signal is m minus 1. So this is blocking matrix. So this blocking matrix, we can actually obtain it if we know the model, the relative transfer functions, okay? Just like we showed before. So if we know the relative transfer function, which is the steering vector. So we know how to find this blocking matrix. Now, the third part, W, is obtained by minimizing the energy at the output. We minimize the energy of ZF, the variance of ZF. And we don't need to put here any constraint. Why? Why don't we need to put any constraint? Because if we want to minimize this variance, it minimizes, it uses the input that of channels that don't contain the desired signal. So if they don't contain the desired signal, we don't need to put the constraint here because it doesn't apply. W doesn't work or doesn't filter the desired signal. So you cannot distort them. So if we solve this, H, so H0, we can solve this. This, we can solve W. So if we, B, the blocking matrix, we can find from the transfer function, relative transfer function. So instead of solving this problem, minimization problem with a constraint, we solved two different problems. One is this, one is this. B, we can derive it. It's quite easy from the relative transfer function. Okay? And then we put it here, so we get solution. So in theory, the solution of this problem, or the solution of this problem, it's the same in theory. In practice, it's not the same because we have some estimates of the correlation matrices. Okay? So how do we solve this? So you see here, we can have infinite number of solutions. So we can find the minimum norm solution. Okay? Here we can find B, and here we can find, actually let's write it more explicitly. So actually we can find minimum WF of the variance of here, which is H0 minus B. Okay, I will write it like this. Phi Y H0 minus B WF. Okay, so I can find this, the solution for this, without any constraint. No need for Lagrange multiplier. So I can find W that minimizes this. Very nice. The thing is, the major advantage, to find solution to minimum variance, we use adaptive filter. So all the methods for adaptive filtering, like LMS methods, least mean squared methods, and normalized, and RLS, and all these adaptive filtering methods, we can use it for W. So we can do it online, in real time. We don't need to do something offline, just like we solve here. Also this, we can solve offline, using least squares, okay? But it's better to use, in real applications, to use adaptive filtering methods. All the LMS family of solutions. Beautiful. Don't you think it's beautiful? Very beautiful. Beautiful work. So this is a very nice contribution to array processing. Actually, things like that are used for beamforming, in speech applications, in communication, wireless communication, EEG measurements. So this work made a very significant contribution to array processing. So it's very important. Okay, so we see that GSC gives us a very nice, attractive way to obtain the MVDR solution in real time, adaptive solution, adaptation of this filter. So if we use offline solution, in theory it's the same. But the structure gives us a way to do adaptive solution, which is beautiful. Now, it's possible not to only give a solution or provide a solution to the MVDR, but also to the LCMV. And this extension is very, very easy, very easy. So instead of one constraint, with the LCMV, we have multiple constraints. So let's see it on the slides, how it provides a very nice solution.